Welcome to this explainer, where we are jumping right into the hidden rules that govern rotational motion. If you have ever wondered why some objects seem to spin effortlessly while others literally fight you every step of the way, you are absolutely in the right place. Today, we are decoding a fundamental law of classical mechanics that dictates pretty much everything, from how you swing a simple hand tool to how massive stars collapse in space. Okay, let's kick things off with a totally counterintuitive paradox that kind of breaks our everyday expectations of gravity and mass. Just picture a ramp. At the very top, you place two objects. One is a heavy, completely hollow metal pipe. The other is a giant but fairly lightweight solid wooden log. Now, if you let them go at the exact same split second, who actually reaches the bottom first? Your everyday intuition is probably screaming that the heavy metal pipe has to win, right? Or maybe you were thinking gravity treats all masses equally, so it is just a dead tie. Well, physics has a pretty brilliant trick up its sleeve here. To figure out the actual winner of this race, we have to look past the scale and look at how these objects are physically built on the inside. To solve this little mystery, we first need to compare standard linear concepts to their rotational counterparts. When an object moves in a straight line, which physicists call translational motion, its resistance to being pushed or stopped is simply its mass. Easy enough. But the second you take an object and try to spin it around an axis, the rules of the game completely change. Mass alone just is not enough to tell the whole story anymore. We have to transition from looking at linear force to looking at torque, and we swap out standard mass for a fascinating new metric called the moment of inertia.
So the absolutely crucial point here is that the moment of inertia plays the exact same role as mass does, just in a spinning world. It essentially measures a body's stubbornness, its built-in resistance to angular acceleration. But here's the major twist. The moment of inertia does not just care about how heavy an object is. It cares deeply about exactly where that weight is hiding. The physical distribution of the mass relative to the axis of rotation changes everything. If you move the mass further away from the center of rotation, the object becomes exponentially harder to spin.
Now, let's look at the math behind this, but we'll keep it totally painless. Instead of looking at a solid object as one big continuous chunk, just imagine splitting it up into millions of tiny infinitesimal cubes of mass. We call these little guys dm. Each of these little cubes sits at a very specific distance, which we will call r, from the axis of rotation. The moment of inertia is calculated by taking the mass of each tiny cube and multiplying it by the square of its distance from the axis, and then adding all of those up. Because that distance is squared, a tiny little cube of mass located way out on the outer edge of an object has a vastly greater impact on rotational resistance than a really heavy chunk of mass sitting dead center.
So looking at the baseline resistance formulas for a few basic shapes, it's wild how vastly different they are depending purely on the object's geometry. A solid uniform rod spinning through its center has a moment of inertia of 1/12 times its mass times its length squared. A solid cylinder is 1/2 mr squared. But look at the hollow cylinder, like a thin hoop. Its value is simply mr squared. Without even crunching the specific numbers for mass or radius, the geometric multipliers, like the 1/12, the 1/2, or the solid 1, instantly tell you how a particular shape intrinsically resists spinning.
Section 1. The power of mass distribution.
Let's use a really practical analogy to feel what this mass distribution actually means in our own hands, entirely outside of the mathematical equations. Think about swinging a standard hammer. If you grab the hammer by the heavy metal head and try to swing the wooden handle around, it feels incredibly light and easy to rotate, almost effortless, right? But if you hold it the normal way, gripping the bottom of the wooden handle and swinging that heavy metal head through the air, it takes some real muscular effort. The crazy thing is, the total mass of the hammer has not changed a single gram. What changed is that the heavy mass is now located much farther from your wrist, which is the pivot point. Because of that, the resistance to angular acceleration spikes dramatically.
Section 2. Shifting axes. Steiner's theorem.
But what happens to our calculations when things don't spin perfectly around their own center of mass? Because out in the real world, objects are constantly rotating around eccentric or offset points. Enter the Huygens-Steiner theorem, or simply Steiner's theorem. This incredibly elegant piece of physics is a total lifesaver. Instead of recalculating really complex integrals from scratch every single time an axis moves, Steiner's theorem says this: if you know the moment of inertia through the object's center of mass, you can find the inertia for any parallel axis. You literally just take that original center of mass value and add the total mass of the object multiplied by the distance between the two axes, squared. Simple as that. I actually love this playful student mnemonic from one of our sources discussing this very theorem. One for all and all for one. It is a nod to the famous Musketeers, but it is a super fun way to remember that in this equation, every single particle of mass in that object shifts together mechanically. You are essentially treating the entire mass of the object as one unified entity moving a specific distance away from that central axis. You can kind of visually imagine taking the axis right out of the center of a cylinder or a rod and just dragging it a distance d away. Instantly, just by virtue of moving that pivot point, you are mathematically increasing the object's rotational resistance. And because of that d squared part of the formula we just talked about, the further you move the axis away from the center, the more violently the moment of inertia skyrockets.
Section 3. Resolving the paradox. The inclined plane race.
Okay, let's take these mathematical tools, the integration, the geometry, and the mass distribution, and go right back to our opening mystery on the ramp. It is finally time to figure out who wins this race. Setting our two competitors side by side, we have the solid wooden log representing a solid cylinder and the hollow metal pipe representing a hollow cylinder. As we saw a minute ago, the solid cylinder has a geometric coefficient of 1/2. The hollow cylinder has a full coefficient of 1. Why? Because in the hollow pipe, every single atom of its mass is packed far away at the outer rim. It literally has zero mass near the center. Therefore, intrinsically, the hollow pipe has a significantly higher resistance to rotation than a solid cylinder of the exact same size and mass.
Now let's look at the energy of this whole system. At the top of the ramp, both objects have potential energy provided by gravity, which is calculated by their mass, gravity, and height. As they start rolling down, this potential energy does not just turn into forward speed. It actually splits into two entirely different accounts. First, linear kinetic energy, which physically moves them down the ramp, and second, rotational kinetic energy, which is the energy required just to make them spin in the first place. This energy split is exactly why the solid log wins the race. When you set up the energy equations, something basically magical happens. The actual total mass and the physical radius mathematically cancel each other out completely. Think about that. A heavy object gets a stronger pull from gravity, sure, but it equally resists moving by the exact same proportion. So the absolute only thing that determines the final speed is the geometric shape, that coefficient of inertia. Because all of the hollow pipe's mass is distributed at the extreme outer edge, it has a massive moment of inertia. It acts like a massive energy hog, wasting a huge portion of its gravitational potential energy just fighting its own resistance to spin. The solid log, on the other hand, has its mass distributed nicely throughout its volume. It uses less energy to spin, leaving way more energy for pure straight-line speed. The solid log always wins, regardless of its weight or its size.
Section 4. Real-world application. Mastering the spin.
Now, this isn't just about rolling logs or textbook math. Human beings instinctively manipulate this exact physics every single day, often without even realizing it. To see how, we have to look at the conservation of angular momentum. This fundamental law states that if no external twisting force, or torque, is acting on a spinning system, the total amount of spin energy, the angular momentum, must remain completely constant. The equation is L, representing angular momentum, equals I, the moment of inertia, multiplied by omega, the angular velocity. Because L is completely locked in, if you physically change your moment of inertia, your rotational speed absolutely must compensate to keep the math balanced.
You see this beautifully demonstrated by figure skaters out on the ice, or even in physics classrooms using a rotating Zhukovsky bench. A person spinning with weights in their outstretched arms has a very large moment of inertia. But the second they pull their arms in tight to their chest, they are moving their mass much closer to the axis of rotation. Their moment of inertia just plummets. And to keep the equation balanced, to conserve that angular momentum, their angular velocity, their actual spin speed, is forced to skyrocket. They become an absolute blur, entirely by manipulating their own mass distribution. So, what you should really take away from this explainer is that this hidden resistance governs quite literally everything. The exact same mathematical rule that makes a hollow pipe roll slower and allows a figure skater to perform a dizzying pirouette scales up to the very cosmos. When massive stars collapse under their own gravity to form tiny, ultra-dense neutron stars, they are effectively pulling their arms in, and as a result, they spin at mind-boggling speeds. It leaves us to wonder, as we look up at the night sky, how else does the simple geometry of mass distribution shape the very structure of the spinning universe we live in? Definitely keep that in mind next time you see something spin.